Section 7.8 deals with something called improper integrals. So this is going to be a two-part video lesson here. The first part, we're just going to take a look at what I consider to be type 1 of improper integrals. But let's revisit the fact that an integral really started, we came about integrals in Calculus 1 from looking at area under a curve. So I just want to go back to a definite integral. So let's say I just have some function y equals f of x. And I want to find the area under the curve between x equals a to x equals b. This area would be equal to the definite integral from a to b of f of x dx. Now notice I have a distinct left boundary and right boundary here. But what happens if I only have one boundary or no boundaries? That is what we'll consider to be improper integrals. So an example here, let's say I have some curve that starts to look like this. And I have a unique boundary off to the left, so let's call that A, but I really don't have a boundary off to the right. I'm actually going to write this as B. Our left or our rightmost boundary just keeps increasing without bound. So if I wanted to find this area, my area technically is going off to the right forever. But notice it is getting smaller and smaller because my function f of x is actually approaching what we would consider a horizontal asymptote. So I would write this first. This would be, the area would be equal to the integral from a to infinity of f of x dx. But how do we work with this? Well, we use, if b is increasing without bound, we bring limits back in to help us out. So we could actually rewrite this as the limit as b increases without bound, and then we could write this as the integral from a to b of f of x dx. So just when you thought we were maybe done with limits, they come back in to help us out with another technique for integration. So let's look at an example. Again, improper integrals type 1 is where we have an infinite interval, which implies when we're looking at the graph, we have a horizontal asymptote. So I want to take a look. Our first example, let's take a look at the function f of x is equal to 1 over x squared. To help us with this idea, go ahead and if you have a graphing calculator, or you could use Desmos, go ahead and graph just 1 over x squared. And you should get a graph that looks like this. So you can clearly see we do have a horizontal asymptote. We also have a vertical asymptote, and we'll address that a little bit later. But let's say I just wanted to find the area from x equals 1 all the way over to the right. So again, this is where my rightmost endpoint or boundary isn't really there. It just keeps increasing without bound. So I would say that the area here under the curve would be equal to the integral from 1 to infinity of 1 over x squared dx. So I use limits here. This is now going to become the limit as b increases without bound from 1 to b of 1 over x squared dx. And then I simply keep the limit notation with this until the very end. And then I'll go ahead and take the antiderivative here. Recall 1 over x squared is the same as x to the negative second. So using just the power rule for antiderivatives here, this will just become x to the negative first over negative 1 from, again, x equals 1 to x equals b. I'm going to just rewrite that to help us evaluate a little bit easier. So this will just become a negative 1 over x from 1 to b. So now this will become a negative 1 over b minus a negative 1 over 1. So now this is where we have to use sort of a reason. We'll reason our way through this. So if b keeps increasing without bound, a negative 1 over b is going to get closer and closer to 0. So this is thinking of it as a -1 over a really large number becomes a really small negative number. So we're getting closer and closer to 0 from below it. So this will become a 0. And then we're just left with the opposite of a -1, so this becomes a +1. Now what's nice is if we ever need to calculate this again, or if this ever shows up in any of our problems, we already know the answer. We don't have to go through this process again. All right, so let's formally define the ways we can rewrite these improper integrals. I'll call this the definition of an improper integral of type 1. So we want to say, if the integral from a to b of f of x dx exists, for every number where b is greater than or equal to a, or a is less than or equal to b, then there's really going to be like 3 cases here that we're going to take a look at. The first is what we just looked at as our example. If I have the integral from a to infinity of f of x dx, I simply rewrite this as the limit as b increases without bound from a to b of f of x dx. So that's really saying we have a leftmost boundary, but we don't have a rightmost boundary for our area. Vice versa, if I'm going to the left forever, I'll still keep b at the top here. So if I have this integral, what I could do now is I'm going to replace a should be the lower part. So a is going to keep going to the left forever. So now this will be rewritten as the limit as a keeps approaching -infinity, or keeps decreasing without bound, again from a to b of f of x dx. But what if I don't have boundaries on either end? What if my integral is going from -infinity to infinity? Well, we separate this. And we could use really any real number. Zeros are the easiest to work with. So we could say that this is the integral from -infinity to 0 of f of x dx plus the integral from 0 to infinity. And now it becomes part of either a or b of f of x dx. But again, 0 could be replaced by any other real number. It depends on the situation. If it's our choice, I would suggest using zeros. And again, all of these are provided that the limit exists as a finite number. Now there's going to be a couple other ways we refer to whether a limit exists or does not exist. So I'm just going to kind of write this out. If we have the integral from -infinity to 0 of f of x dx, and the other one here, the integral from 0 to infinity of f of x dx, these are called convergent if the corresponding limit exists, meaning if we do the calculation and we actually get a real number, a finite number here, and then divergent if the limit does not exist, meaning if we end up getting infinity or -infinity. Okay, so let's jump into some examples. For this first one, and a lot of the problems on WebAssign are just going to ask us to determine whether the integral is convergent or divergent, and if it is convergent, to actually figure out that value. So let's determine if the integral from 1 to infinity of 1 over x dx is convergent or divergent. All right, so we have an example like that part A from the previous page. So we're going to rewrite this when our upper boundary of our limit of integration here is infinity. We're going to rewrite the limit as b approaches infinity from 1 to b of 1 over x dx. All right, so remember the antiderivative of 1 over x in this case is going to be the natural log of the absolute value of x from 1 to b. So now this becomes the natural log of the absolute value of b. But in this case, because b has to be greater than 1, they're both positive, so I really don't need the absolute values anymore. So the natural log of b minus the natural log of 1. And we know the natural log of 1 is what? 0. So we just get the limit as b approaches infinity of the natural log of b. Now to help us out here, I'm just going to make a quick sketch of y equals the natural log of x. Now at the beginning of this class, we talked about inverses. So y equals the natural log of x is the inverse of y equals e to the x. And here's our graph for y equals e to the x. If I were to reflect this over the line y equals x, I would get a function that looks like this. So as b keeps increasing without bound, our graph keeps going upwards forever. So this would actually give us infinity, which means the limit doesn't exist. So therefore, the integral from 1 to infinity of 1 over x dx is divergent. All right, another example here. And just like our very first example, if we ever come across that 1 over x as our function, again, we know it's always going to be divergent from the integral from 1 to infinity. Let's go ahead and evaluate the integral from negative infinity to 0 of x times e to the x dx. So we're going to first rewrite this using a limit here. Now notice the bottom value here is the negative infinity. So this is where we say it's equal to the limit as a approaches negative infinity of the integral from a to 0 of x times e to the x dx. So now based on our expression here, we're going to go ahead and use u substitution. We'll give this a try first. Actually, I mean integration by parts because we have a product here. So we're going to let u equal x, and then dv is going to equal e to the x dx. So then du is equal to dx, and v is equal to e to the x. So again, we're going to rewrite this. Keep this in brackets though, as we use integration by parts. So remember, it's u times v, so x times e to the x. And within this, we have to still evaluate this from a to 0, minus the integral from a to 0 of v du, so we have e to the x dx. So first, if we substitute a 0, and we're just going to get 0, then minus, I'm going to put the 0 in here to make sure we understand we still have to subtract a times e to the a, and then minus the antiderivative of e to the x is e to the x, and again from a to 0. So this will just become negative a times e to the a minus, and inside here we'll get e to the 0 minus e to the a. Now to help us out here, I'm actually going to write this as negative a over e to the negative a, because I have a negative infinity here, it's going to be a lot easier to reason through this. Then e to the 0 is just 1, and then I'll end up getting a plus, and I'm going to write this as 1 over e to the negative a. So it would be plus e to the a, but then I'm going to write this as 1 over e to the negative a. So here's what we're looking at. If I have negative a over e to the negative a, and a is approaching negative infinity, then I'm just going to write it like this to help us visualize it. This is negative a. This is a constant over a really large number, which approaches 0. The same thing over here, 1 over e. This would be to a very large number, so that will also approach 0. So these two will go to 0, and I'm just left with a negative 1. So that this integral would be convergent because it actually turns out to be a nice value here, not an infinity. Okay, another example here. Let's do something that's like part C. Let's go ahead and evaluate an integral from negative infinity to infinity of 1 over 1 plus x squared dx. So this is where I'm going to take this and separate it. We'll start with negative infinity. Again, I'm going to choose 0. 1 over 1 plus x squared dx, and then plus the integral from 0 to infinity of 1 over 1 plus x squared dx. So this first term is actually, we're using that part b, so I'm going to write this as the limit as a approaches negative infinity of the integral from a to 0 of 1 over 1 plus x squared dx. And then this will become the limit as b approaches infinity of the integral from 0 to b of 1 over 1 plus x squared dx. Now what I'm going to do is find them individually. So I'll come back to this problem though, but I'm going to start with this part right here. Let's go ahead and figure out what that is. So the antiderivative of 1 over 1 plus x squared, hopefully you guys are recognizing it, it's actually an inverse trig function. And it's inverse tangent. So we could write arctangent, or we could just write tangent inverse of x from a to 0 here. So we're going to have the inverse tangent of 0 minus the inverse tangent of a. All right, so this is where we need to know our unit circle. Or the graph of tangent might help. So if you recall, when we're trying to figure out values of inverse tangent, remember we're trying to find angles, and we have to stay between negative pi over 2 to pi over 2. And if we're at 0, the only way to get 0 in between negative pi over 2 to pi over 2 is when we take tangent of 0. So inverse tangent of 0 is still 0. I'm just going to draw the graph real quick here. So if we're at negative pi over 2 to pi over 2, this is what the graph, we're going to have vertical asymptotes here. And this first point is what I'm talking about. So tangent of 0 is 0. So inverse tangent of 0 is still 0. Now, as a keeps approaching negative infinity, my radian measure is getting closer and closer to negative pi over 2. So then the inverse tangent of a, as a approaches negative infinity, still have a minus, is going to be negative pi over 2. So now this becomes positive pi over 2. Now, since I got a finite number for this, I'm going to go ahead and evaluate the limit as b approaches infinity of the integral from 0 to b of 1 over 1 plus x squared dx. If for this first part I got an infinity, we would be done. We don't have to check the next part. We would say either infinity or negative infinity, that this would be divergent. So this is going to become the same thing as far as the antiderivative goes. But from 0 to b. So we would have inverse tangent of b minus inverse tangent of 0. So I already know this last part here is just 0. So as b keeps increasing without bound, now we're back up to the graph, we're getting closer and closer to pi over 2, so that this would equal pi over 2. So now we put these two back together so that the integral from negative infinity to infinity of 1 over 1 plus x squared dx is going to equal pi over 2 plus pi over 2, which is pi. We'd say, therefore, the integral is convergent. And that value is pi. All right, this next example is going to lead us to a very important fact that's going to help us throughout the next part. So we want to know for what values of p is the integral of 1 from 1 to infinity of 1 over x to the p dx convergent. Now if we go back to our previous examples, we saw when we had 1 over x squared as our function, it was convergent, but 1 over x was divergent. So we're going to kind of generalize this. So let's write this out. So we know from the previous examples that if p is equal to 1, then this is the integral from 1 to infinity of 1 over x dx is divergent. So let's assume that p does not equal 1. Then we'll have the integral from 1 to infinity of 1 over x to the p dx is equal to the limit. We'll use b here because the infinity is at the top. So the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx. To make this a little bit easier, I'm going to rewrite the function as x to the negative p. And then use the power rule for antiderivatives. So this will become x to the negative p plus 1 over negative p plus 1 from 1 to b. All right, but what I'm going to do is factor out. I'm going to rewrite negative p plus 1 as 1 minus p. It just looks a little bit nicer that way. And then I'm going to factor it out from this fraction here because it's just a constant. P is a constant. So I'm going to have 1 over 1 minus p. And then I'm actually going to flip that numerator so it becomes 1 over x to the p minus 1. Remember, I'm going to take the opposite of the exponent here when I go to take the reciprocal. And this will be a lot easier to evaluate and reason through. So now this becomes the limit as b approaches infinity 1 over 1 minus p. And as I go to use the fundamental theorem of calculus, we'll have 1 over b to the p minus 1 minus 1 over 1 to the p minus 1. Which will just be 1 here. So if p is greater than 1, then p minus 1 has to be greater than 0. And then we come up with the following. Then the limit as b approaches infinity of 1 over 1 minus p times 1 over b to the p minus 1 minus 1. So this is the part I want to focus on. So that means p minus 1 is positive. So that means we're getting 1 over, as b keeps increasing without bound, this is becoming 1 over a very large number, which is just going to 0. So then I end up with 1 over 1 minus p times a negative 1, which really just becomes 1 over p minus 1. So the integral converges. If p is less than 1, then p minus 1 would be negative, and the limit as b approaches infinity of 1 over 1 minus p times 1 over b to the p minus 1 minus 1. So let's take a look at this part right here. So if b keeps increasing without bound, and then this is a negative number, so I'm really getting 1 over b, we'll just write it this way, to a negative number, and b is a really large number, then this becomes b to a positive number. So this is infinity to an even larger number. So as b increases without bound, b to any exponent is also going to do the same. So this is going to equal infinity. And the interval diverges. So we'll say, therefore, the integral from 1 to infinity of 1 over x to the p dx is convergent as long as p is greater than 1, and it's divergent if p is less than or equal to 1. Alright, so we'll stop there in this video. In the next video, we'll talk about type 2, do some more examples, and then talk about something called a comparison test for improper integrals.